Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 55 and the topic we will be covering in this is basically a 3-5 HEMT and its modeling. We will look into the application of HEMT, also referred to as a high electron mobility transistor, and the material which we will be referring to is a 3-5 semiconductor, right. As we already know, HEMT is a field effect transistor which is used to offer a combination of no noise figure and high level of performance at microwave frequency. Let me break it down into smaller pieces for your better understanding. The idea here is that, as the name suggests, is basically a device which provides high electron mobility, right, because of certain phenomena, and when it does so, it provides a larger current as compared to its traditional counterpart of other FETs. But this high electron mobility transistor does have a advantage of very low noise figure, right. The noise figures are relatively low and high level of performance, when I say, because the current is very high, the switching speeds are also relatively high, and primarily they can work at microwave frequencies, right. So, any high frequency modeling or high frequency switching, HEMT finds a use to that. Now, the key element of an HEMT is a specialized PN junction. PN junction. So, if you remember your basic PN junction theory, then we had referred to the PN junction theory and told you that in a PN junction you had a P type and an N type being generated, right, and because of which there was a depletion region. If the doping concentration was same on both the sides, the depletion thickness on both the sides were equal, right. However, we will see in the later slides that if you can use a material, two different types of materials with different band gaps, then I can create a potential well at a particular point where you can store large number of electrons, and the scattering there will be relatively very small and the mobility will go on increasing. So, that is the basic underlying feature of an HEMT, and this concept is known as heterostructure, right. This is known as heterostructure junctions, which means that heterojunction basically means two or more than two type of material form a junction at a particular point, and what they do is that they use the very fact that the band gaps are different for different materials. They try to create a well, a potential well in that particular domain, and once you try to create a potential well in that particular domain or in that junction, you basically allow a large number of electrons to stay there. Not only that, if you apply a bias, it will start moving without too much amount of scattering, and therefore the mobility increases. Typically, instead of a PN junction, we use metal semiconductor Schottky junction. And why? Because they are relatively easy to fabricate and allow for much stringent control on the geometrical tolerances. And that is the reason HEMTs have found a use in most of the cases where requirement of very large currents are required, and not only that, you do not want to also sacrifice on the frequency of operation. With this, let me give to you the basic structure of a gallium nitride based HEMT. So, this is basically a gallium nitride based high electron mobility transistors. Mobility transistors. So, this is gallium nitride based designs, right. Now, it has been observed that GaN actually has got two advantages mainly. One is its high frequency application, and the second one is its high power. And generally, both the things together you do not find in any of the devices, but for GaN it is giving you a better device. Now, given the excellent high power and high frequency application of HEMT, many researchers have attracted towards GaN based devices, which was actually first done in 1993. It was first invented in 1993, this GaN based HEMT device. Uh, Now, because of now the application areas where you find GaN HEMTs are in radar systems, right? High power radar systems. You also find use in communication systems, base stations, right? Communication systems and base station where you require very high power of output to be generated. A new mobile communication system. So these are the application areas, and this is the characteristics which you see for a high power device. Now, if you look at the structure here, this structure here, then let's go step by step across the structure. You will see you have a source contact here, you have a gate contact, and you have a drain contact here, right? So, as any FET device, HEMT will also have source, gate, and drain contact. However, what we are doing is we are now having an aluminum gallium nitride layer and a gallium nitride undoped layer. We are sort of using it as a sandwich layer, right? And there is a buffer, a substrate layer. This is known as a substrate layer, right? This is the substrate layer which you see. Now, typically the dimensions of the source contact, this is source contact which can be a metal contact as well, is approximately 0.3 to 3 micron. Gate to source extension region is approximately 0.3 to 1 micron. The gate length is 0.1 to 3 micron. Between gate and drain is larger than gate and source. So, gate and source are relatively closer as compared to gate and drain. Gate and drain is between zero point 0.5 to 50 micrometers, and the source contact, drain contact is exactly symmetrical, as whose dimensions are between zero point 0.3 and 3 micrometer. Now, this blue colored domain which you see, this blue colored, this small sandwiched blue color here, dark blue color, is where you are able to concentrate the two dimensional electron gas. So, you see you have this 2 DEG. DEG means two dimensional electron gas, right. So, it is basically a two dimensional electron gas, which is, so you have a layer of electrons being formulated, and this goes right through the device structure itself. Uh, Now, depending upon the molarity of aluminium gallium nitride and gallium nitride, which is basically undoped, I will be able to generate the width of the 2D electron gas. Typically, very small widths are maintained in there. We also ensure that these drain contacts and source contacts have less number of traps available to you, and we do proper annealing techniques to remove those traps, so that the 2D electron gas remains as typically requires a very high mobility. It will always have a high mobility if the traps are not available at the source and drain contact at this region and at this region of operation. In these two regions, we do not want any heavy traps to be developed. The idea is, since GaN is basically a large band gap material, and AlGaN means, when I say it's aluminum gallium nitride, is a relatively a smaller band gap. So, when these two band gaps materials are stuck together, I get a 2D electron gas, and I will show you as we move ahead. Now, this effect of two structures being lumped together is known as a polarization effect, and that results in high electron density, right. So, you please understand that you are therefore basically confining within a small region of three dimensional region a large number of electrons, and these electrons will be therefore sort of repelling against each other, and as a result what will happen is that once they repel with respect to each other, they will have less amount of scattering within themselves. Now, they are therefore used for high power amplifier design, because their breakdown voltages are relatively very high, right. You require to give a large amount of reverse biases in order to break down, and therefore it's adequate for high power amplifier. Further, it has got a much larger heat capacity, which means that the heat capacity is very large. It can actually have a property of absorbing heat to a much better extent. There are two techniques available in this fabrication. I will not go into details of that any further. One is MBE, which is molecular beam epitaxy, and MOVBE we use, which is metal organic vapor beam epitaxy we use. Typically, the band gap, as I discussed with you, for GaN is 3.4 eV and has got a much higher thermal conductivity as compared to a conventional device. Let's look at the operation, the concept of polarization now of the GaN. Now, I will show you how it works out typically. Maybe this diagram will help you to show. I will come back to that slide later on. Now, as I told to you, HEMT utilizes heterojunction between two semiconductor materials to confine electrons in a triangular potential well. How does it do that? If you look very carefully, I have got this layer Al GaN, right? Then you are sandwiched between aluminum nitride and then you are sandwiched a gallium nitride core. So, this is the gallium nitride core here, and this is the aluminum nitride, and this is aluminum gallium nitride shell, and this is we are looking from top to bottom. We are looking from top to bottom. So, we are going from this aluminum nitride and then gallium nitride core we are looking. So, we are going from top to bottom, not sideways, right? We are going from top to bottom and trying to find out the conduction band edges. Now, you very well know that we have already discussed in our earlier classes that for the device to be in equilibrium, the Fermi level should not change with respect to x, which means that the Fermi level should be constant across the board in order to have a constant, or we need in order to have a dynamic equilibrium between the two, which means that if there would have been a change in the Fermi level, I would have expected to see a current, but since there is no current in the transverse direction, I am assuming that the Fermi level is always aligned. As you can see here, since the Fermi level is perfectly aligned along aluminum gallium nitride and the gallium nitride core, and since gallium nitride is typically an n-type material, the Fermi level is very close to the conduction band, whereas AlGaN is more closer to the valence band, and therefore this is more of a p-type. So, it is basically just like a p-n junction, but just Schottky because this behaves as a metal junction. Look at aluminum nitride layer here, and exactly what is happening is that there is a steep, almost a steep fall in its conduction band edge here, and then it goes like this, and then it starts to rise up. The conduction band edges starts to rise up. Why? Because on the gallium nitride core you didn't give any potential, right? You give a potential on the gate side. That gate side potential forced to change the shape of aluminum nitride conduction band in such a manner that your conduction band falls just below the Fermi level. So, all these areas where I have marked red is basically my 2D electron gas, and this 2D electron gas, so this is the cross sectional area I have cut. If you go inside your desktop or laptop screen, you will see that this is sort of a thin layer of 2D electron gas right running from source towards the drain. So, if you want to find out the total electron, you need to integrate from source to drain for the 2D electron gas here. The advantage of this one is that the scatterings are very low here, and that is the reason it is almost behaves like a ballistic phenomena, if totally not like a ballistic phenomena. It almost behaves like a ballistic flow of charge carriers. So, I have this aluminum gallium nitride shell, and then we have got an aluminum nitride and followed by electron gas here, and we have Cb and Ef, the Fermi level here. What we are not considering in this case is that we are not considering that the Fermi level will change because of certain variations in the dimensions of the device or temperature and so on and so forth. So, we are assuming it to be an ideal sort of ideal Fermi level, which is pinned to a value which is given by this formulation here. With this, what we have done is, therefore, now unlike what we have learned in silicon technology where you require very high doping, because when you do the high doping, the depletion region thickness will be very small, and you can have effective layers of charge carriers, though they are not mobile there. Here we do not rely upon the doping of individual layer of devices. We rely more on the discontinuity of the band edge to formulate a 2D electron gas. So, the disadvantage of high doping will be that because of temperature variation and so on and so forth, the doping variations might change. The doping itself might change within as you move across the device dimensions, and therefore, it is difficult to control the 2D electron gas population by doping, and it's better to therefore use a structure where you can actually do a doping or discontinuity in the conduction band. So we refer to this as spontaneous polarization plus piezoelectronic polarization, which gives rise to approximately 10 to the power 13 to 10 to the power 15 centimeter square per volt second carrier per volume carrier concentration. For HEMT, typically this is the value which you require. So let's go one by one now, and then we'll go to the modeling of gallium nitride based HEMT. But most of the microwave transistors which we use, they are typically the backbone for all your communication systems for 5G and beyond, right? So if you look at the left hand side, sort of schematic here, then we have microwave transistors, which are basically transistors which work in the microwave region, right? They are divided into two parts, right? And the first part is basically FET based, field effect transistor based, and the second part is BJT based or bipolar transistor based, right? Both have its own relative advantages and disadvantages, but that's how you divide the two sides of the same coin of microwave transistors. Now, bipolar is again subsequently divided into silicon bipolar, right? Silicon BJT, which we already know. We also know gallium and arsenide HBT is heterostructure bipolar transistor, indium phosphide HBT, silicon germanium HBT. HBT is heterostructure bipolar transistor. Heterostructure bipolar transistor. Right, and the same concepts applies for the field effect transistor also. Within the field effect transistor, we have gallium arsenide MESFET, metal semiconductor field effect transistor. So this is basically a Schottky sort of contact which you get. Then you have got gas HEMT or gallium arsenide HEMT, within which we have classical HEMT, we have P type and N type HEMT based on gas, and then you have indium phosphide, gallium nitride, and silicon MOSFET, of course, right. This to a larger extent is a workhorse for all your current digital technologies and analog technologies, whereas indium phosphide and gallium HEMTs are primarily meant for high performance microwave region of operation devices. So typically the microwave transistor is basically divided into a bipolar technology based transistor and a FET based technology transistor, right. And both have their own domain of specific working. Uh, MESFET, MOSFET, and BJT are composed of only single semiconductor material. Now, if you look at the lower cartoon or the lower diagram, you will see that typically 1G worked till 1979, 2G worked with 91, 3G at 98, 4G 2009, 5G as we have already finished and we are entering into 6G domain. What we are looking beyond 6G is 2030, beyond 5G we are looking into it currently, right. The advantage which we get is of course a high sampling rate, therefore communication is much easier and faster, but sustaining such a high frequency model without compromising on the power, that's the main basic challenge for any microwave transistor based design. We have already discussed this point time and again. I will quickly go through them, that you have a monolithic HEMT or passive network for phasor applications, and you have high power and high frequency gallium nitride HEMT for microwave communication applications. We also use indium phosphide high power, high efficient HEMT amplifiers for high frequency applications. Now, let me come to HEMT models and large signal model and small signal model, and look into the various modeling parameters which people use nowadays as far as gallium nitride based HEMTs are concerned. Now, we know that we need to have an accurate and reliable device model. That is an essential component. It is necessary for efficient and reliable delivery of GaN based MESFETs or HEMT devices. HEMT devices. And right from devices to circuit, we require the whole area to be covered in this case. In addition, the device model needs to have good convergence. When I say good convergence, I mean the time taken to converge is very small without compromising on the accuracy of the model, right. So that is very important for any model to work fast, which means that you want a fast simulation time, very fast convergence rates, but without compromising on the accuracy of the model which you are going to choose, right. Let me show you the various modeling techniques which are available to us in this case, right. What are the various modeling techniques which are available to us in the compact modeling case? When we do a model development, HEMT model development, we look into the large signal equivalent circuits, and various compact modeling methods available for HEMT are table based approach, empirical model, machine learning based model, and physics based model. Now, interestingly, we will go one by one and explain to you what these approaches are. But interestingly, I will start with some of the models and we'll go one by one. Before we go to the model part and explain to you the details of it, let me sort of, if you plot log of frequency here, log of frequency, right, log of frequency, and this is in gigahertz. So, I have got 1, 10, right, 1, 10, 100, then 1000 gigahertz are there. And if you plot saturated output power, and this will be in dBm, then it is seen that typically this goes, gallium nitride goes from this point to this point. This is for gallium nitride. Gallium nitride has a switching power approximately, it goes from 60 to around 40, which means that for a gallium nitride at relatively high frequencies of operation, your saturated output power actually starts to drop down, right. So, it is almost, so this is a dBm drop I am trying to impress upon you. There is a drop taking place in a linear fashion. Similarly, if you take gallium arsenide, you will see that it goes right from, so this is, let me say 1, right from, it goes from 1 and it ends up approximately here. This is 1, it ends all. So, you see the range, this is for gallium arsenide. So, the range till which, the frequency range till which it works for the same change in the value of your output power is much larger in case of it. So, dynamic range is much larger in case of gallium arsenide as compared to gallium nitride. A good idea for you as a learner will be to see the reason why this dynamic range is relatively higher for gallium arsenide as compared to gallium nitride. Similarly, if you look at CMOS powers are relatively very small. So, powers are almost 20 dBm smaller as compared to a conventional power. So, if this is CMOS, right. So, that is where the CMOS loses its flavor, silicon based CMOS loses its flavor when you talk of high frequency, because the reduction in power is relatively very large, right, and that goes down to a low value. This goes even up to lower as 20 dBm at very high frequency range. So, these are all from literature which you can achieve, and you can get good amount of output from these design problems and design. You can actually do a forecasting which of the elements can be used for what purposes, and that is the reason this graph is relatively an important one. However, so we come to learn one thing is that the dynamic range of gas or gallium arsenide is much larger, dynamic range of gallium nitride is relatively smaller, but has got a much larger power to be delivered outside, and therefore they are used for all practical purposes. The various available compact model methods are table based, sort of a lookup table based. You have an empirical model, you have a machine learning based model, and then you have a physics based model. Now, let us look at the development of gallium nitride HEMT in a timeline. So, we will take this up, this model development we will take it up in the next lecture. Let me recapitulate what we learned till now. We learned, at least in this lecture, about HEMT. functionality, how band gap engineering is being done in order to generate a two-dimensional electron gas within the structure itself, within the HEMT, and how HEMT therefore has got a very high performance design because of very high current without compromising on the breakdown voltages. This breakdown voltage is also relatively high in case of a gallium nitride. Now, therefore, the overall sort of takeaway from all this discussion is that for all gallium nitride based HEMT, the output characteristics are the best. So, what we will do in the next class is look into the various modeling development of HEMT, look into the chronologically how the modeling development went ahead from large signal model, and then we will finish up with the various factors or the applications of HEMT. With this, let me thank you all for your patient hearing.